Welcome everyone. I'm Jim Corkins and we are continuing on with Module 3.0. We are now into how voltage interacts with electric fields. So what's that relationship? All right. So we have already seen this slide before and I just want to point out that we had this as negative E dot R. Right? And that dot product is going to be very important. But this is just a reminder, and we're going to be dealing with capacitor electric fields a lot because it makes things a lot easier to understand. However, just to go over this, we are going to calculate voltage due to an electric field is negative E dot R. The electric potential is parallel to the surface and perpendicular to the electric field. Okay, so this is the electric potential line for positive 20 volts. Notice it's parallel to the surface and it's perpendicular to all of these pink electric field lines. All right, now it always goes that this constant electric field will create a constant voltage, meaning this, that if the electric field is equally spaced, the voltage lines will be equally spaced. Unlike charged particles, they create an electric field that drops off over time, so those electric field lines are getting further and further apart. Well, that's also happening to the voltage lines. In a capacitor, the central potential line is always 0 volts. Okay? And we have to view this as this is the high plate. So if you're standing here at the bottom looking up, this would look like a flat surface. So it would look like this. So you would be standing here as a charged particle and you'd be kind of looking up a nice flat surface. And this would be the positive plate, and you would be standing on the negative plate. All right? Now, I had mentioned, again, I'm going to mention again, this negative E dot R is very important. Okay, and we're going to get into why that is important right now. Because that dot product is actually saying that the electric field and the path that you take or the displacement that you take have to be parallel to each other. Okay? And so, for example, if you walk on this plate right here, if you're walking on this electric potential line and you're walking straight down, you'll notice that your voltage isn't changing. Okay, so the only way your voltage actually changes is if whatever component of your motion has to be parallel to the electric field and perpendicular to those voltage lines. Okay, so to illustrate this, here we have a capacitor, right? And the path that we're taking is this delta R, right? So if you take that electric field, okay, so we're going to do a change in voltage. And incidentally, our change in voltage starts at positive 20 volts. It ends at negative 20 volts. So right here, this path that it's taking, that's going to be a negative 40 volt change in voltage. Okay, now we know that this motion right here is not perfectly parallel to the electric field, and it's not perfectly perpendicular to the electric potential lines or voltage lines. So in order to calculate this, we actually have to take in this case, the cosine of this, R cosine theta. And so this right here, that's the hypotenuse, this is theta, this is the adjacent to it. This actual direction is going to be our cosine theta. Okay? So, for example, if this was, I don't know, 4 meters long, that path, delta r. Okay, so this path is 4 meters long. Okay, so hold on one moment. So if that path, delta r, is 4 meters long, okay, hold on one moment. I'm going to put negative 40 volts here. And that path is 4 meters long. Okay. Well, the cosine of that, and I'm going to write this, cosine theta. So this negative 40 volts is going to be equal to negative E dot, and they're moving to the right, so this is a vector component right here, and that is going to be 4 meters cosine of theta. Okay, so if we need to calculate this electric field, incidentally, this is going to be 2 meters, and if this is, let's call this 60 degrees, just to make our life easy. So if this is 60 degrees right here, this is going to be 2 meters. And so negative 40 volts equals negative E dot 2 meters to the right. Should put a plus in front of this, plus. And so negative 40 volts over 2 meters, that's going to be equal to negative 20 volts, which is equal to negative E. So therefore, the electric field, the change in voltage, sorry, I shouldn't have put, so therefore, this is volts per meter. Therefore, the electric field is a positive 20 volts per meter. Okay, so that is correct. But let's look at what happens if we calculate this incorrectly. So that's negative 40 volts. We know that's negative 40 volts. And I'm going to put negative E dot delta R. And I'm going to just leave it like that. So negative E, and our original path is 4 meters. And so if we end up dividing both sides by that 4 meters, what we get is an electric field that is equal to 10 volts per meter, or to the right 10 volts per meter, which is incorrect. So you must calculate the electric field, the part of the path that you take or displacement that you take, that only that part that is parallel to the electric field is going to actually contribute to the change in voltage. The other part of this, the sine part of this, which is going to be straight down, which is delta R sine of 60 degrees, if you notice, that is just straight along that path. So that is not going to, that's actually, there's no change in voltage along that path. Okay? Incidentally, sometimes you see weird curved electric fields like this. This would be the electric field that you would have if you're on like a inclined plane, right? And so the electric field might be going up and to the right. And so if you think about this, and this path is delta R, only this part of the path is responsible for the change in voltage, because see those voltage lines? So that again is delta R cosine of theta. So wherever that angle theta is, you have to think about what part of that, if the path is not parallel to the electric field lines, you have to find at whatever part of that path that is parallel to the electric field lines, you have to make that your change in voltage, right? That's your actual path. And in this case, that's negative E delta R cosine theta. Okay? So that's an important point that I wanted to get into. Now, another thing that we should get into is graphing voltages. Okay? So we might have mentioned this before, but the slope in a voltage versus distance or voltage versus displacement graph, that is the electric field, right? Well, actually, that's the inverse of the electric field. So the negative of the electric field. And I'll talk about that for a moment, right? So let's plot this slope right here. So we have a slope, this is going to be the 0 volts, right? So this is basically that electric, well, the capacitor just to its left right here. So, but anyways, this first voltage line is really high, and then it's going to fall to 0 here, and then it's going to go down here. Okay? Now, if we look at the slope of this line, and we kind of did it right here, okay, there's a change in voltage of negative 40 volts, right? And negative 40 volts, and we worked this out to be 2 meters. Well, that change in voltage, which is this graph, is change in voltage. This change in voltage over change in R, that is the negative electric field. So you have to take the opposite of that, right? And so I'm thinking about this equation, negative E delta R, and we're going to divide both sides by the delta R, and that's negative E. So if you're given a graph of, in this case, where the change in voltage goes from positive to negative, okay, you have to think about it for a second, right? Because that's a positive slope right there. But in order to relate this to the actual electric field, you have to take the negative of that slope. So what I think of is, I call this just the change in slope right there, right? And then I do a quick calculation. I put that change in slope right there, and then I multiply it by a negative. So in this case, right here, if this was positive 20 volts, and this is negative 20 volts, and that was across, I think in the problem, 2 meters, well, the slope of that line, you're dropping by 20 and then dropping by another 20. So that change in slope is resulting in a negative 40 volts, and it took 2 meters to do that, right? So you get a negative 20 volts per meter, right? Well, if you notice, this electric field that we're basing this on both of these graphs, that electric field is pointing to the right. So what you have to do is kind of have to artificially change that. And how you do that is you take that negative E, you say negative 20 volts per meter is equal to negative E. So E is then equal to positive 20 volts per meter. And so you get a rightward pointed electric field. Okay? Now, regardless of whichever way you're looking, doing these problems in your homework, you have to identify a point at which it starts and which it ends. In this case, I'm having it start right here, okay? which if this is 0 meters, this could have been 2 meters in, and then 4 meters, and then 6 meters over here, right? So this is 0 meters right there. So that difference of 2 meters. So I would have started right here. That's my initial. And then that 2 meters ended right here. So that inverse, you have to establish a starting position and ending position. And that starting position could be considered like a 0 point on the potential line, right? So you could just correct this. It really doesn't matter because we're talking about a change in position right here. So a displacement rather. So anyways, and then we have to establish a coordinate system. Our coordinate system is up is positive to the right, up is positive y, to the right is positive x, to the left is negative x, and down is negative y. And then you just basically solve the problem from there, okay? So that helps you map it out. But let's go ahead and practice this procedure right here. So we're going to do a couple problems. And these are tutorial problems, and they're going to be at the end of your tutorial in 3.3. So they're going to be a part of that introduction to electric potential energy. And they'll be, and part of the reason why is I want you to be able to still be thinking about voltage and electric fields, but then introduce the concept of electric potential energy, because that is voltage as well. All right, let's go ahead and do this problem right here. So here we have a problem where it looks like it starts off at -6 and ends at +2. Okay, so starting at -6 volts, it ends up at +2 volts, and it's going to take 4 meters to do that. Okay, so the first thing we're going to have to do, let's establish the voltage lines here. I'm going to go ahead and label this -6 volts, because it looks like, if you notice, it's moving to the right. So if this is 0, and then you got 1, 2, 3, 4, 5, and 6, right? Then that means this plate on the left, that has to be the -6 volts. Okay? So how I know this plate on the left is negative is because this starts off at -6 volts at 0. So I'm going to label 0 right here. Okay? Okay, so moving to the right, these are positions. Anyways, they're distances that you move, and it's moving just to the right. All right, now for -4 volts, -2 volts, +2 volts, +6 volts, +4 volts, and +6 volts. Okay, now this object it's going to be just moving in a straight line. I'll make sure you know that in yours. It starts off here, and it doesn't matter what height it is. So I'm going to have it start right here at about the 4 meter height. Right, so right about here. And then it's going to move directly to the right 4 meters, starting at -6 volts, ending at +2 volts. Okay? And so now we could actually calculate the electric field at this point, right? So what is the slope here? Well, I'm going to do a real quick estimation of this slope. So I want to know what delta V over delta M is equal to here. and so it's moving in the positive direction, or positive voltages towards the positive plate here. Okay, so it's moving, so that it's rising by 2, 4, 6, 8. So it changed in the positive X direction. So it's a positive 8 volt change in voltage across 4 meters. So that's basically positive 2 volts per meter. And that's just the change in slope here. Okay. Okay. So that's the path it's taken. All right. Now, you'll notice, even though the path is taken this way, and we know the rule, the electric field has to point from away from the positives and towards the negatives. That means the electric field lines need to be pointing to the left. Okay, everywhere. But this is, we've kind of basically calculated this to be a positive voltage. And again, this is the reason why in that equation it's a negative E dot R. Okay, so that change in voltage over change in meters is equal to negative E. And so this change in voltage is positive 2 volts per meter. So the electric field is going to be equal to negative 2 volts per meter. Negative 2. Just to get into the details of this, there's another way to do what we just did. Okay. And I'll just organize this real quick, and I'm going to show you what I'm talking about. Okay, this is a line, right? And we could, and we actually did it right here, just we did it with our heads, but we could apply a linear fit to this. Y is equal to mx plus b, but the y-axis is voltage, and we're trying to predict final voltage. Okay, the initial voltage is right here. That's the initial voltage. And here, this is delta V over delta X times the change across the x-axis, right? So in this case, our final voltage is positive 2 volts. We're going to calculate the slope, so this is what we're going to solve for. The change in distance is going to be positive 4 meters, and it started out at negative 6 volts, right? So pull the negative 6 on the other side. So I'm going to go up this way with the math. Actually, I don't need to go that far. Positive 2 volts, add 6 volts to both sides, plus 6 volts equals change in voltage over change in distance times positive 4 meters. Put a little times there. And then this is just going to be positive 8 volts. So we're going to get positive 8 volts divided by positive 4 volts, and that is our change in voltage, right? Or change in X, which is just going to be positive 2 volts per meter, right? So that's another way to do this. For me, I just think it's easier just to do your everything right on the graph, because if you count, you go, oh, okay, I have a positive slope, and I've just counted. I'm going 2, 4, 6, 8 up, and then 4 over, rise over run. So I went up 8 volts and I went over 4 meters. That's positive 2. Now you got to take the opposite of this. So whatever this sign this works out to be, it's opposite day. So this is going to work out to be a negative 2 volts per meter. So that would work out to align with the fact that our electric field has to be pointing to the left. So our electric field is pointing to the left here. Now let's graph it. So all the problems that we're working on are constant electric fields. So this is going to be an electric field that is pointing to the left the entire time. There you go. All right. So this is the first page on your tutorial. Okay. Another problem on our tutorial that I'd like to do, and we could go over how to go from the electric fields to create voltages and create this capacitor right now. Let's just do it real quick. Now, in this case, we're given the electric field is pointed to the left across 6 meters. So let's go ahead and write that electric field pointing to the left across that 6 meters. Whoops. So it's pointing to the left. It's pointing to the left everywhere. So I'm not going to put it everywhere here. But you get it. So the electric field has to be pointing to the left. That's pretty easy to answer right here. Now, it says it starts off with an initial voltage of negative 12 volts. So that has to be on this side. So let's go ahead and start off by calling this negative 12 volts right here and negative 12 volts right here. Now, the area of these boxes right here, that is the change in voltage. Okay, so I'm going to zoom out a little bit so I could work some mathematics, right? So change in voltage is negative E dot delta R, right? And if you're in my calculus class, you would do dV equals negative E dot delta R, right? Integrate both sides. That's the area of this line. So this area, this E dot delta R, is this area right here. Okay? And I don't want to do equations in this. I want you just to use your head. What shape do you see? What is this shape from here that I'm outlining right here? What shape do you see? Triangle, square, rectangle. What do you see? Rectangle, right? So this is the electric field. So I'm going to fill this out a little bit. So this is the electric field. So this is negative E, which is going to be negative 2 volts per meter. Okay, so this is E, which is, we got to put that negative E in here, and this negative still is out front. Okay, and how far did it go? 6 meters, right? So this area is describing a rectangle, which is going to be positive 6 meters displacement. So what we're going to work out is that, this is in my way, the change in voltage in this case is going to be negative times negative is positive, so that's going to be 2 volts per meter times positive 6 meters, which is going to be positive 12 volts. So the change in voltage here is going to be positive 12 volts across 6 meters. Positive 6 meters. And that is an important statement. And there's a lot of ways to approach these tutorials, so try not to worry too much about, am I doing the right thing? Just do your best and try to be creative if you can. So on this graph, this is going to go from negative 12 volts and it's going to change by positive 12 volts across 6 meters. That means the end of this has to be at 0, right? If it's going positive 12 volts, then it's starting at negative 12 volts. Well, positive 12 minus 12 is 0. So this line for the voltage is going to be right here, which means if I number this, this has got to be 1 and this has got to be 6, so this is probably like 12. Okay, so you have to number it so it makes sense to you. And actually 0, 6, and 12. Yeah, now that makes sense. And that means over on this other plate, this side's got to be positive 12. So the path that it took, it had to have started here and it ended right here. And so that is our change. That is our delta R. And I forgot to write delta R on this over here. So hopefully this is getting you thinking about how voltage is related to electric fields and how it actually looks in a concrete, example. Okay. So, and the biggest problem that I've seen students make is when they're dealing with electric fields, is they forget the negative part. And this is also meant to emphasize how you have to flip that that electric field or the math for it, so the actual case does work out making sense, right? And so this electric field has to be pointed to the left, and that means if we're moving to the right, we have to be moving to the right in this case, so the math does work out. Okay, let's do one last one. Actually, let's do both of these. I suppose we can do both of these. So in this problem, it looks like we're starting off and we have a 0 voltage, and it ends up going to negative 2 volts. And then something weird is happening here. Okay? So in this case, we have to be thoughtful about how we're doing this. So there's two different things going on. Obviously, the slope of this line is 0. So the change in voltage of this line is equal to 0, which means the voltage isn't changing for a distance of 1 meter. Okay? So this starts out with a 0 voltage, so it's going to start out along this point in the line, and that's also the 0 place on this as well. And we're going to be moving to the right, so this is going to be positive 1 meter, positive 2 meters, and positive 3 meters right there. And then so this must be negative 1. I'll get rid of the meters there. So positive 1, positive 2, and positive 3. So this must be negative 1, negative 2, and negative 3. So sometimes you might have to number these where the positions are weird. Okay? 0 is not always here. it's kind of where you, what the problem is telling you to do. Okay, so in the y direction, it doesn't really matter in the y direction, but let's try to start on something that makes sense. So let's start at the 4, which is right here. Now, we're going to be moving to the right. And where we're moving to the right, we're going to end up with a negative voltage. So our final place is, for this first part, is going to be right here. So positive 2. So if we're moving to the right, positive 2. And if that's true, then this has to be negative 6 volts right here. So the first part of this, we're moving to the right, and that's our first motion right here. But then after that, we have this motion right here. That means it's got to be moving down a distance of about 1 meter, right? So if this started out at 4, it's got to end at about positive, it's got to end at 3 right here. Actually, let's make it move upwards. That way everything is going to be. So after it moved this first part, now it's going to be moving upwards 1 meter. And that's the other delta R. So that's this line right here. Okay. And so let's calculate this. All right, let's calculate the electric field. The only part that we could actually use to calculate the electric field is the red line, because the black line isn't going to help us calculate the electric field. So again, we're going to just do our math right on here. This thing is dropping, and I'm going to change this color to black. Delta V over delta X is equal to 0 volts per meter for this black line slope. This red guy's slope, well, it's dropping by 1, 2, 3. So its voltage change over delta X is going to be negative 6 volts across 2 meters. So this is going to work out to be negative 3 volts per meter change in slope. But again, we got to turn this in to a positive. So this is going to be a positive 3 meters, positive 3 volts per meter, which means our electric field has to be pointing to the right. This is saying that our electric field has to be pointing to the right. So let's do that. You can just do a couple lines. It doesn't have to be a big deal. Or you could just add arrowheads to these pink lines. There you go. So we've marked this up. Now let's go over here. Well, this is going to be a constant positive 3, which is right here. Over the distance, I'm sorry, I should be using red. Over the distance of 2 meters. And then something happens, and now the path is now going upwards or downwards. I chose upwards in this case. So again, the electric field is going to be pointed to the right, and that means this is the negative plate, and this is the positive plate. Okay. I really hope you do this, because this is going to help you a lot. All right, let's move on to our last part of our little tutorials. So in this case, we're given the actual path, which is this length right here. And we don't know that length, but we do know it makes a 30-degree angle. and it looks like it starts off at, well, actually, it starts off at positive 8 meters right here, and it looks like it's ending at positive 2 meters. Okay, so it actually went 8 meters to 2 meters, and that's only in the y direction. So we know this distance here, it actually went down positive 8 to positive 2. So what is that? It went down a distance 6, is it 6? 2, 4, 6, yep. So this is 6 meters long, okay? Now, we need to create a V versus R graph. We need to create an E versus R graph here, okay? And we're going to also indicate the electric field as in volts per meter. And we don't need to indicate the direction of the electric field here because the voltages are laid out above here. Okay, now, what we're going to have to do to figure this out, okay, is again, if the path is this red path, okay, and he's moving at an angle of 30 degrees to this y-axis, well, we need to figure out this distance right here, because this is the only part of the path that contributes to a change in voltage, right? And if I write this out right here, you can see the voltage is changing by positive 8 volts at 8 meters, and it's ending at negative 4 volts at 2 meters, right? So we're going to have to do some mathematics here, okay? Well, we have this distance right here, which is 6 meters, and this is 30 degrees, so this is our angle, 30 degrees. We need to figure out this one. So we need the side opposite our angle of 6 meters. So this side right here is going to be the opposite side. We have adjacent, so when I hear opposite over adjacent, I think of tangent. So the tangent of 30 degrees is equal to the opposite side over the adjacent side, which is 6 meters here. So 6 meters tangent of 30, okay, that's going to be our actual displacement delta R. So we're about to figure that out. It's going to be a weird number. 30 second function tangent times 6 equals, I'll try to make sure yours works out to be a whole number. Mine's 3.46. Wow. So this is positive 3.46 meters to the right. So about 3.5 meters, right? To the right. So it will end here on both of these graphs. I'm going to try to make sure everything works out to be whole numbers for you guys. Okay? Now, let's go ahead and let's calculate the electric field. So if you look at this, it starts off at positive 8 volts. Positive 8 volts. It ends at negative 4 volts. Across that 3.46 meter. So this, it's dropping by 2, 4, 6. So it's dropping by, so change in V is, this is going to be negative 6 volts over change in X, which is 3.46 meters. That's so weird. Okay. So let's calculate this. So 6 negative divided by 3.46, negative 1.73. So this is going to work out to be negative 1.73 volts per meter. Okay. which, again, we have to make it positive. So that's going to work out to be a positive 1.73 volts per meter. Okay? And now we just have to plot that, which is about right here. Okay? So I hope you learned a lot. Again, I thank you very much for working on these tutorials and helping you. And let's go ahead and start doing some conceptual problems, okay? So from doing that, I bet you're going to be great at these two conceptual problems that we're going to do, okay? So let's do these two conceptual problems before we finish out, okay? Now, you have an electric field here that is a changing electric field. So this couldn't be caused by a capacitor or not. This has got to be caused by some kind of weird point charge or something. So because the electric field is dropping off to 0 across 1 meter. Okay, so the question is what is the total change in voltage if the initial potential is 0? So they're basically saying we want to know what the final voltage is, and we'll plot this in the graph here. V final, if our initial voltage is 0 volts. So that's what we're kind of asking here. So we have to figure this out. It's one of these answers. Okay, so the area under this line is the negative of the electric field, right? So delta V is going to be equal to negative E dot delta R. And so this area, I'm seeing a triangle here. So the area of this is going to be this. This whole area is this. Okay? So this is E dot delta R. Not negative E dot delta R. That's E dot delta R. So let's go ahead and figure that out. And we'll put it right in here. So I'm seeing a triangle. So all triangles are half rectangles. So I'm seeing 2,000 times 1. So positive 2,000 volts times 1 meter divided by 2. So this is going to work out to be positive 1,000 volts. Voltmeters. I'm so sorry. Positive 1,000 volts, because this is 1,000 volts per meter times 1 meter. Okay, so 1,000 volts. So I'm going to just put 1,000 volts right here. So the total change in voltage is negative 1,000 volts. Okay, so our final voltage is going to be negative 1,000 volts. Okay, now putting this in the graph right here, it's got to change by 1,000 volts. So it's starting right here, and then we know it's eventually going to reach a negative 1,000 volts. Now the problem is this electric field is dropping off. So this is starting off with positive 2,000, right? Well, the y-intercept here is the initial slope here. So the positive 2,000 times negative is going to start off with a really negative slope. And then that slope drops off to 0 as it approaches this. So this is going to look something like this, where it eventually drops off to 0. Okay? That's our first conceptual question. Let's do the next one, and then we'll be done. here we go. We have a voltage versus distance graph, and we're going to have a position here, XA, and XB is right there. And they want to know at which point is the electric field stronger. And what I think they mean is where the electric field number is the largest, not negative or positive. Like a negative 2 volts per meter is the same thing as positive 2 volts per meter when we're talking about strength. So which one of these is going to have a stronger or larger voltage? The answer is not this one. There is enough information to figure this out. So go ahead and try to answer this question. Pause the video. Well, the slope here, again, is the electric field. And the steeper the slope, the stronger the electric field. So if you look at this, XB has a very level slope in comparison to XA. So XA has the stronger electric field. Okay, well, thank you very much for watching this video. We're going to go ahead and in the next video we're going to begin electric potential energy and do an introduction to that. And you'll be asked at the end of the tutorials for 3.3 to complete problems similar to what I just did over here. Let me go to them. Along with some electric potential energy problems. So it's a good tutorial. You'll learn a lot. Have a great day.